Yeah, so a natural question is, how good is the SDE at describing SGD? And mathematically, I think the first thing that comes to mind is, what does it mean to describe SGD? Okay, so how can we understand the quality of the SDE approximation? So here I have two trajectories, and I kind of did this like rather poor keynote drawing to show that they are actually distributions of trajectories. And what we know is that neural networks can have a very similar performance with very different parameters. So how can we actually meaningfully understand whether two trajectories approximate each other? Well, one concept to borrow from classic mathematical analyses is to introduce a test function. So maybe a test function is something like gradient norm, but also a very practically relevant test function is test accuracy. So I will note here that this G test function needs to obey some mathematical assumptions that are probably not true for test accuracy, but are probably true for something like gradient norm. So that's just something to keep in mind, that we've kind of already started drifting away from the very practical question of test accuracy and started moving towards something more abstract. Although you could argue that gradient norm is perhaps the thing you need to track in order to understand generalization. So what we do is we pick this test function and we compute its expectation on each of the iterates in SGD and SDE. And we measure the distance between those, and we basically want to have a bound on this weak on those distances, the maximum of those distances. So this is actually known as a weak approximation, and this right-hand side, crucially, is a function of the learning rate. So you may be thinking, okay, then the approximation will grow stronger as the learning rate gets smaller, but in that case, the stochasticity will be gone. We're back in the gradient flow kind of limit. And that's a fair point. So the next question to ask is, does this SDE actually approximate real-world training? And before I move on, I just want to highlight one of the interesting mathematical features here is that picking the rescaling to go from discrete time, meaning each iterate of SGD, to continuous time, meaning each so-called iterate of SDE, is actually a crucial part of the analysis. And this time scaling is something I'll talk a little bit more in the future. So in general, I'm kind of not getting too much into the math, but if there are any like technical questions, I'm more than happy to discuss those. Okay, so are these SDEs good approximations for finite learning rate training? So we have some initialization, some distribution of discrete trajectories. This could be SGD, we could have used a different optimizer, or anything. And then we also have a distribution of trajectories given by some SDE. So what we propose is that you can actually construct this trajectory that interpolates between these two, and that naturally is itself a distribution over trajectories. So how do we do that? What we do is we scale the learning rate down by a hyperparameter L, and then we measure the mini batch loss for two different batches. That's what this gamma 1 and gamma 2 are here. And we take a weighted combination of those, and we say that that's actually our loss now. So what's actually going on here is that we want to preserve the expectation while amplifying the variance. If we amplify the variance of the gradient, meaning the variance of the noisy gradient, that sigma term that I was talking about before, if we keep amplifying the scale of that, then even as we take the learning rate to be very small, we can ensure that there is such a large amount of noise that the limit will still be stochastic. And the crucial point here is that you can actually run this algorithm, right? So the algorithm that we saw, or the SDE that we saw for SGD, which I will just go back to quickly over here in this corner, we actually can't simulate this on a reasonable time scale with a reasonable compute budget, because we'll need the full gradient at every discretization step. And then we'll also need this noise covariance computed, which will require estimating, drawing many mini batches and estimating the moments of that distribution. Okay, so we have this simulation which we can run, and it's actually a discrete trajectory. And the thing to note about it is that it actually runs L times slower, right? So the learning rate gets scaled down by L. So you need L times as many steps to kind of simulate one step of SGD. I just put one experiment here, but our paper has a lot more. If you run this simulation and you increase L, then you see that the trajectories are roughly converged to the same place. And here we chose the test function, like I said, to be validation accuracy, but we also have things like the norm of the gradient noise or the norm of the gradient itself. And so the key idea here is that we can use this hyperparameter L to interpolate between SGD and the SDE. So if we set it equal to 1 in this equation, we're essentially just taking the gradient from one mini batch, and so we're just doing SGD. As we take L to infinity, we'll get to the continuous limit while amplifying the noise, like I said, so that even when the learning rate is very small, we still have a stochastic process.
Sadhika, sorry?
Yeah.
So the gamma 1 and gamma 2, these are just two realizations of your of the mini batch choices. So are these SDEs?
Right.
Are you talking here about an SDE, or are you talking about the actual SGD?
This F is just your loss function. So this is like the loss evaluated on two different mini batches.
Okay.
So this entire procedure yields a discrete trajectory, not a continuous one.
Okay, so that means between two time steps, you actually keep the mini batch constant.
At every time step, you will sample two mini batches and do this combination. So you'll burn through the data like twice as fast.
Yeah, but they're kept constant, like in the SDE limit, like you switch kind of the mini batch infinitely often in any kind of finite time step, right?
Oh,
like if you let
see.
So you don't do that here, correct?
Yeah, that's right.
Okay, thank you.
Well, so I want to make sure I'm understanding. So at time step t, I will draw one batch and I'll draw another batch. And then at t+1, I'll draw yet another batch and yet another batch. But yeah, so over the time corresponding to this L times worth of continuous time, you are fixing the mini batches instead of sampling them like infinitely fast like you would in an SDE.
Yeah, that was my question. Thank you. Yep.
Yeah. Okay, so back over to kind of the practical side of what the SDE can tell us. And I do want to say, like, studying the SDE is in its own right a very interesting mathematical question. And I am more trying to couch the entire analysis in things that are happening in the world today. But I also think that studying the SDE further is like definitely a very interesting thing to do. And I will show further how those types of analyses can be done. But here's an example of something the SDE can tell us. So what we have here is this is a network trained on ImageNet. And basically in this top left-hand corner, we have a very small batch size. And at the bottom right-hand corner, we have a super large batch size. So this is corresponding to the setting that I was talking about, where you have an increasingly distributed setup and you're trying to train very fast. So the author's goal actually in this paper was to train a network in 1 hour that generally would take maybe like a week or something like that. So they get a bunch of GPUs together and they increase the batch size, and then they try to train. So here, the orange curve is the baseline with the small batch size, and that, of course, does super well. We can see that as we start to scale up, which are these blue lines, then we see that actually the performance starts to degrade. Okay, so what does this have to do with the SDE? Well, one thing the authors propose in this paper is the linear scaling rule, where you scale the learning rate proportional to the batch size. And actually, that is what they're doing in these experiments to even get it to scale to like this level. So where does this rule come from in the SDE world? This comes from, so recall this is our SDE right here. If we scale B, the batch size, to kappa B, then this covariance will scale by 1 over kappa. And so that means that we need to scale the learning rate to kappa times the learning rate in order to preserve the constants in this SDE. So this is a very straightforward, I guess, mathematical analysis of this SDE. But you can see how having a limit that actually can describe gradient noise and the scale of gradient noise can be very practically useful for modern day machine learning. I mean, highly distributed training settings are things that are of ever increasing interest in our day and age. So that's kind of one way that the SDE can be useful, and I'll get into some other ways later. But I just want to say that actually another thing that you get is that the SDE implies the linear scaling rule. If the SDE approximation is good, then the linear scaling rule should hold. So that means that in this lower right-hand corner, the SDE approximation is actually not good. So why is that? Well, doing some kind of old school differential equations, error analysis, backward error analysis, can tell you when this SDE is going to diverge significantly from the discrete trajectory. And characterizing that case actually tells you, okay, like in this case, you're not guaranteed to have the scaling rule hold. Okay, so let me give a more practical illustration of that. So here what we do is we predict the failure of the scaling rule. So these three columns are some different architectures, and they're all trained on the same data set. What we have is that we do one baseline run. So that's kind of this blue dot that's sort of in the middle of these graphs. And using that one run and a condition that we derived, you can actually extrapolate when the necessary condition for the scaling to hold will fail, which is this red shaded area. Or sorry, it's this red dashed line. So this means that the necessary condition for the linear scaling rule, meaning the necessary condition for the stochastic differential equation to be a good approximation, will no longer hold. And this condition, if you're curious, kind of relates the gradient noise scale to the norm of the gradient. And you can imagine why that's true, because when we take the limit to get the SDE, we're basically blowing up the noise so that we can still measure it at an infinitesimally small learning rate. So in that case, if there is actually not that much noise in your procedure, for example, you used a large batch size, then the SDE is not going to be the correct limit. Maybe you should actually be using gradient flow or a different continuous limit. So that's kind of an interesting outcome from this whole thing, is that we started from a very theoretical point where we said, you know, we wanted a continuous thing. We like working with continuous things. And we first got something that didn't have any noise in it. Then we added some noise to it. And now we've actually arrived at the point where we can say, like, practically speaking, if we don't have enough noise, things will fail. And we can predict that with just one baseline run here. Okay, so I want to give a quick note on adaptive optimizers. So this is the optimizer called Atom. It looks quite intimidating on first glance, if you have never seen it before. But basically what it is it's SGD with some bells and whistles. So it's SGD with some momentum. So momentum is like keeping an exponential moving average of the gradient. And then there's a normalization term. And also you have a moving average of the second order moment. So once you have this momentum, you have the second order moment, you apply some simple normalization and scale the gradient accordingly. Oh, sorry, something's in the chat. Could you explain the notation circle with the dot? Yes, so circle with the dot is element-wise product. So these will all be vectors in the same dimension as the number of parameters in the model. So when you apply this normalization, you need to do it like element-wise. That's all that the notation is. Okay, so first I would just like to say, if you have not really thought about adaptive optimizers or heard of them, they're a bit of like the rage right now, because these are the best ways to train transformers, which are, of course, the architecture of the moment. And also, I think in terms of optimization theory, it's never really been well understood what's going on with these types of optimizers, where we clearly have some more information. Like we have some information about how the gradient has been changing recently, and maybe even an estimate of like the second order moment of how the gradient has been changing. But it's not clear how having all this information and normalizing accordingly is going to actually like benefit you. Okay, so how can we take SDEs to adaptive optimizers? When we want to derive the SDE here, there's a big challenge facing us, which is how should we take the learning rate and then also these moving average coefficients to their limits? So these three things are usually hyperparameters that you set. And kind of the funny thing is people set beta 1 and beta 2 and never look back. And most code bases probably have the same exact choice of beta 1 and beta 2. But when we have these three hyperparameters and they're all dictating, as you can imagine, the parameter movement in terms of continuous time, we need to find a limit that can model stochasticity and adaptivity. So we now have kind of this double challenge here. And if you're interested in seeing kind of how we handle that or what different cases arise if we take them to their limits at different rates, this paper that we wrote on the SDEs and scaling rules for adaptive gradient algorithms has some information. But what I will say is ultimately we overcame the challenge and we came up with some SDE, and that SDE actually yields a different scaling rule, which is a square root one. So we scale the learning rate by a square root of the batch size scaling factor. And we also crucially find you need to scale epsilon, beta 1, beta 2. So here's another example where these values generally are ignored by practitioners and just set to something, set it and don't touch it. But actually, if you do adjust these properly, then you can go to a much larger batch size without losing generalization. So just some experiments, these may be foreign to you, they may be familiar to you. We can go all the way to like a batch size of 32,000 or 8,000 when we're training language models. So like I said, Atom and in general adaptive optimizers are really the optimizer of the moment because transformers are so popular. But do we actually know what's going on with them in optimization theory? I would say definitely not. And if that's something that you are interested in working towards, I would be happy to chat more about that, because I think this adaptivity is like something that should give us a benefit, but it's actually been very hard to pin down what that benefit is. Yeah.
Just to get the point of what you're saying. So you're saying we can increase batch size, and the advantage of doing that is that we also increase learning rate. Is that the idea? So we converge faster, or why do you want to be able to increase batch size?
Yeah, that's a good question. So there's kind of a very practical view of it, which is that you will train on a very distributed cluster. And so let's imagine that you have 8 GPUs, and now you're training this one network. Each GPU has a minimum batch size of 1. So whereas before you could set the batch size to 1, the batch size now will be 8 at minimum. So this is one kind of perspective, that there's a minimum batch size. The other thing is that if you are actually having 8 GPUs at your disposal, then you want to maximize, in some sense, the throughput through the model. You want to process as many data examples as you can at a time. So the x-axis on all of these plots is the epochs, meaning the number of times that each data point was seen. And that's something that you want to fix. But you don't need to fix the number of steps. You don't need to fix other things. So if you can plow through the same data set 8 times as fast, 16 times as fast, or even thousands of times faster, then that's a huge benefit in terms of just efficiency.
Okay, thanks. I only kind of understand why, but should I really imagine that I have like 1,000 GPUs or something? Is that what you're saying? Or
Yeah, so although it sounds a little bit crazy, I think there are many practical settings actually do have thousands of GPUs. But yeah, I think like it's a little bit hard. It was a bit hard for me to understand too, from a mathematical perspective, why one would want to scale the batch size. But I think the easiest thing is if you take it for granted that you can only see the data 10 times or something. And then you're trying to do that as fast as possible. Then you're trying to see as much data as you can at each step. That may be the like best way that I can convey it. But yeah, I think like, so if you go to like OpenAI or Facebook or Google and so on, like to train at large batch sizes is really essential, because you'll have these huge data sets. Maybe you've scraped the entire internet and you have like that entire corpus to get through. And the more data you can process meaningfully, right, without losing performance, within one forward pass, the better, because GPUs or TPUs or whatever they are very capable at parallelizing these operations across the batch dimension. So you want to fit as many examples as you possibly can onto the chip, and then the operation happens very quickly, even though you're doing it on thousands of times as many examples. Yeah.
Can I, maybe since we sort of ask questions, can I ask sort of follow-up or related question to this? So if I let B go to infinity, then the correct continuum model would be just, classical deterministic gradient descent. So you're looking at, finite batch size, so there's a central limit theorem, over all those kind of gradient evaluations that gives you the noise, and you can, characterize the covariance. Am I correct that you sort of now, well, you have a drift term and you have a diffusion term, and if the diffusion is too small and your drift is sort of non-Lipschitz, which is the case here, then, if you just do basically Euler-Maruyama, which is your, like the sort of, the numerical approximation of the SDE, you would sort of, you can overshoot, right? You kind of, your drift is too strong and you can overshoot, and you're not going to converge, right? So Euler-Maruyama is going to be very bad, and then you would need like a very tiny, small, uncontrollable learning rate, I guess. So but can't you sort of normalize in doing something like taming, or tempering, I think it's called, or taming, like where you just divide your gradient by 1 plus, learning rate times the norm of the gradient or something like this? Have people tried this? I mean, that's what people do for SDEs.
Right. Yeah, no, that's a great question. So I think it kind of goes, so I want to say first about the Euler-Maruyama thing. That is exactly what we're like trying to address with this proposed simulation algorithm. And yeah, so you do have this problem where like if the drift and the diffusion terms are not suitably scaled or like comparably scaled in some meaningful sense, then you can have this like process that is very difficult to simulate or capture. Yeah, so I think that like people have definitely tried normalizing the gradient, and normalized gradient descent in and of itself has birthed its own world of optimization analyses. But I will say that in the context of SDEs and in the context of the scaling rule, that's actually not something that I've heard of people trying. So that's definitely something that can work, I think. Yeah, so the thing also is that here, when we do this type of analysis, the long and short of it is that, well, just to summarize the proof sketch, it's something like you have a time horizon of eta steps, and then you want to get an error that's at most eta squared, so that you can kind of get this eta dependency in the ultimate bound over all the steps. So here, like when you are doing that one step, kind of saying that each step is relatively close between these two things, that actually requires a lot of conditions on both your test function and also the gradient and also the drift and so on. So yeah, that's, I guess it seems that those conditions are satisfied in practice, but those conditions are quite restrictive and do indeed need like some kind of like Lipschitzness, and the covariance itself needs to be well behaved as well, so that your distribution, the parameter dependent noise distribution, changes in some like reasonable way over time. But yeah, so that's what I think. I don't know if that answers your question. It was like a mishmash of ideas, but
no, thanks. Yeah.
Okay, great. Okay, so I want to talk a bit about generalization, which I guess I have kind of been touching on by showing all these plots of test accuracy, but have not touched on rigorously. So one hypothesis about generalization is that it actually arises in the late stage of training. So here's this plot, which I actually got from some collaborators. So far, everything we have been talking about is in this like 1/eta time horizon, where we are, actively minimizing the loss and things are changing and the gradient is non-zero. Then we reach some point where the gradient actually is zero. But because we're in this over-parameterized regime, we're actually on some connected manifold of local minimizers. So all of these points will have a gradient of zero. And so this is where the generalization question comes about, because we're doing great on the training set now. And everything that we do from this point onwards basically is just changing how we do on the test set. So one interesting framework that's very recent actually is to describe this movement on this manifold using another SDE. Okay, so let me see if I can, yeah. So when the loss is very small or you're like on this manifold, this is its own SDE, what's shown in black here. And if this SDE was just doing its own kind of thing, like I guess that would not be super interesting. But what they actually find is that in some settings, during this second phase, there is this very slow movement shown in dashed red over here, like a limiting diffusion that is minimizing the sharpness of the solution. So there's this black super noisy process, but on a very slow time scale, it's moving in the direction of a low sharpness solution. Now, who cares about sharpness? And by sharpness, by the way, in deep learning, people are alternately referring to either the largest eigenvalue of the Hessian or the trace of the Hessian. But here, if we minimize the sharpness of the solution, this is actually thought to improve generalization, which is actually not something that's very well understood or characterized. It was an empirical finding where the authors tried many different measures that could possibly correlate with generalization, and they found this to be one that relatively reliably correlated. But that was maybe 5 years ago, so who knows now. But yeah, so in terms of like mathematical view on this, this is very interesting. Like you now have these two SDEs. You have one that's characterizing when the gradient is actually non-zero and the other when the gradient is zero. And this has many applications. So some questions that have been answered using this framework are like, why do certain distributed SGD variants generalize better? So what I mean by this is like, suppose you had, again, 8 GPUs and each GPU was taking its own SGD steps. And then every once in a while, the GPUs would kind of sync and like average their parameters or something like this. So this is once again a case where you're trying to save some computational cost. And you would think, okay, this is not nearly as good as all the GPUs synchronizing every single step, which is the standard paradigm. But actually, it does generalize better when you do these local steps. This is called local SGD, where you do local steps and then you synchronize every once in a while. So why is that? Well, that's something that can be understood through this limiting diffusion. Other similar questions are like, how does normalization improve generalization? And does momentum always provide a generalization benefit over standard SGD? And so on. So I would say that if you're kind of interested in this SDE view of optimization, the first part of the talk was really establishing the basics. As I would say, like, here are some optimizers, here are the SDEs, and scaling rules are great. But this is really where things are starting to get interesting, because we're talking about something that we're not able to characterize in basically any other way. We need to have this SDE on the manifold. Okay, so a quick summary and discussion of like the first half of this. And I realized that that actually took 45 minutes, so I will zip through the rest of it. But I think this is the more mathematically interesting part of the talk anyways. So the SDE seems to be a great way to model early and late stage stochastic and adaptive training dynamics. And a typical consequence of it, if you want to just derive the SDE and then try to get your paper published, is to give a scaling rule, where when you increase the batch size, this changes the covariance very predictably, and you can scale the learning rate or other optimization hyperparameters accordingly. So what's next in this world? The first is, does sharpness actually dictate generalization? Why is that? And what about some steps in early stage training or medium stage training, or whatever you would like to call it? Another question is, how do we go from this per parameter trajectory, where we've just described each parameter using its own little SDE, to a functional view of the network? So maybe we want to actually say something meaningful like, oh, this super wide network learns low rank features, or something like that. So these types of statements have been made about very specialized architectures, settings, data sets, and so on, but have not been actually made in this very general setting with SDEs. I think a large reason for that is, well, the SDE has not been around that long, but also because the people who are working on SDEs are pretty happy just deriving scaling rules. But I think that mathematically speaking, this is really where I think optimization could use a boost, is to go from a per parameter description to a functional description. And of course, we still can't generally answer, why does gradient noise help generalization? All we've done basically is try to preserve it and ensure that it's there in the cases where it's threatened. So I'm happy to answer any other questions on this part of the talk before I move on.
I had a question. In the second SDE that you showed, once you hit the, so does this have some sort of a scaling that is also related to the scaling that you did before?
Yeah, that's a great question. So this actually requires like a different time scaling in order to be able to observe both the fast oscillations and the slow ones, if that makes sense. So you still need this black thing to be a stochastic trajectory, but you also need to be able to study this like red limiting diffusion. So the time scale of that is indeed like something you have to be careful about when doing the analysis.
So in some sense, you can go out of the local minima if the scaling is not appropriate.
Yeah, exactly. Yeah. So one of the papers that described this used this limiting diffusion, they actually scaled the loss to be like square root of the loss, so that they could control this time scale carefully. Yeah, so that's a great question. Okay, I can move on now. So up next, so SDEs are kind of agnostic to the model initialization, but the modern deep learning regime is something entirely different from all the plots that I've kind of shown so far. So mystery number 2 is, how can we characterize the pre-training and fine-tuning paradigm? Which, if you don't know the paradigm, I will tell you now. Okay, so this is how like many of the state-of-the-art models, especially language models, which I'll kind of focus on here, are trained. So you get a pile of books or a bunch of data from the internet, and you train a transformer to predict words. So given some context, some incomplete sentence or complete sentence, predict the words that can follow this. You then take that pre-trained transformer and you do something called fine-tuning. So now you actually have this model that can generate sentences. And a priori, this seemed to be not actually the end goal of NLP, though these days with chatbots, it seems like it might be a very useful end goal. Actually, what people wanted to do before was to solve these language understanding tasks. So maybe you get a movie review, and then you need to classify the sentiment. Was that a good movie or a bad movie based on what the person wrote in the review? And one thing you can do to make this easier is to add a prompt. So you can add a prompt that makes it look a lot like the pre-training task. So you might get a movie review like, the script was super boring. Then if you add a prompt, it was, and then you ask the model to predict the next word, then if it predicts great, you can say, okay, the model knew that was positive sentiment. Or if it predicts terrible, then you say, okay, the model said that it was terrible sentiment. Okay, so one natural question is, why is there no overfitting during fine-tuning? We have transformers these days with billions and billions of parameters, but when we actually get down to fine-tuning, we have maybe a couple dozen examples in some settings. So one intuition about this whole paradigm is that the pre-trained model basically understands language. So fine-tuning is just making a slight change to the model. But of course, as mathematicians, we ask, how can we make this rigorous? What does this actually mean? Okay, so bear with me here because I'm not certain if people have seen this framework before. But so if you include a good prompt, then you induce what's called kernel behavior, which I will describe as gradient descent, where the gradient of the model is not updated. So the gradient, the derivative of the loss with respect to the output of the model can change, but the gradient of the model output with respect to its parameters should be fixed. And why do we care about this? Well, actually, that means that if you take a bunch of steps of gradient descent, this is equivalent to performing kernel classification with a special kernel. And anytime kernels are there, we're excited because it's like linear algebra instead of having to do all this SDE stuff. Okay, so this was a very seminal paper in 2018 that introduced the neural tangent kernel. And basically what they said is if you had an infinitely wide, randomly initialized network, and you trained that with SGD, then the result of the training could be simulated by doing kernel classification with this neural tangent kernel. So what's this special kernel? This special kernel is just it uses the gradient of the model on a given input as the feature. And then of course the kernel is the inner product across these features. So what I want to say here is that actually the theory community became very invested in this NTK kind of view. And then it was kind of like, okay, let's take a step back. Like, do we actually believe that when you're training a deep network from scratch, the gradient is not changing, or can it even be modeled meaningfully that way? And basically the conclusion was like, no. So people moved on to, more complex things like SDEs and so on. But now we're back because we are fine-tuning a pre-trained model. And so it's actually kind of believable that the gradient of the model output with respect to its parameters doesn't change over the course of fine-tuning. And one thing that's great about the kernel view is that you actually get an initialization dependent view of what your model is doing. Because now in this case, when we apply it to fine-tuning, this phi of s that we compute is the gradient of the pre-trained model on a given input. So we have an initialization dependent view and architecture dependent view of the optimization dynamics during fine-tuning. So there's some math work that needs to be done to extend this to the case where you no longer have the random initialization and you actually are fine-tuning with something like Atom, which we saw was like its own spaghetti of equations. But what's the takeaway here? So I don't want to get too deep into the NTK world, which has a lot of rich theory in it. And I would urge you to check it out if you're interested in this view. But the takeaway is that fine-tuning is actually performing just a very simple mathematical operation on the network. You have this like huge transformer with billions of parameters. And even though it's learning and adapting to a new task, it doesn't need to change most of those parameters because there was so much learning that occurred during pre-training. And one thing that's nice is that now we can study the kernel and we can just get direct insights into fine-tuning. So I'll give an example of what these insights kind of look like just to give a sense. So there's this very popular empirical method called LoRa. So let's say we had a linear layer. We give it an activation, and during pre-training, we just do the classic matrix vector multiplication. When we fine-tune with LoRa, we fix this W and we introduce a low-rank pair of matrices, AB. And we only train that AB. Okay, so why does LoRa matter? Why is it important? Like, I will defer that discussion. But what I will say is, mathematically speaking, this looks like drastically different. So imagine you're doing this throughout your network, just some fully connected layers, you're freezing the weight and just adding a low rank modification. So how does this procedure actually affect the black box of fine-tuning? Well, if you take the kernel view, then fine-tuning with SGD is equivalent to classification with the SGD kernel, the NTK kernel. And then we actually can just use Johnson-Lindenstrauss because these are randomly initialized. So we have random projections of our gradient. And so the inner product should be roughly preserved. And that's basically the theorem that we show in our paper, is that if the kernel view describes fine-tuning, then doing this procedure does approximately the same thing as fine-tuning. Now, I know that this crowd may not find LoRa or have heard of it or, find it to be very interesting. But I think the key takeaway here is that once you have a kernel, you can do all these very simple operations that actually correspond to very complicated things in the network. But then with the kernel, you can simplify what that operation did to the optimization dynamics and actually get a very clear-eyed view of what's going on when you're fine-tuning. Okay, I will just skip through the experiments. What I want to say here is that the optimization will depend heavily on the task and the prompt, but most of the time the gradient is nearly constant. So this fine-tuning is like a simple operation. And I just want to highlight that like this insight is from experiments over many tasks. Okay, so on to the last section, which I will zip through. If gradient noise is beneficial and fine-tuning is performing such a simple operation, okay, so we're synthesizing the past 1 hour of this talk, basically, then can we use very cheap and noisy gradient estimates to fine-tune the models instead of doing backpropagation? So that's exactly what we do in our new paper. So we fine-tune the language model using only forward passes. So you may be familiar with this SPSA, simultaneous perturbation stochastic approximation, I think. Maybe I switched simultaneous and stochastic, but you basically get this gradient estimate, which is just the difference between the losses when you perturb the parameters. And this should look hopefully very familiar from calculus, because when we take the limit, when epsilon goes to 0, this becomes like very close to the derivative definition. So the first thing to observe is that this is an unbiased gradient estimate, and that's natural because Z is a Gaussian. And so this method has the same memory footprint as inference. We're doing 2 forward passes, and then we're going to compute this gradient estimate. A naive implementation may have you saving this Z, but we get around that by saving the seed and resampling. Okay, so what's my point about this? Now, if we can actually use this algorithm, then we can reconstruct this gradient estimate very efficiently. We only need the random seed for Z and just this difference between the losses. And this can reduce our gradient communication cost. And also, this loss doesn't need to be differentiable anymore, whereas before with backpropagation, it needed to be differentiable. Okay, so, the results are good, and I will kind of like just leave it at that for this talk. But adding a simple prompt is actually crucial. So recall the prompt is something that made the downstream task look a lot like the pre-training task. So why does this algorithm work? The classical analysis says that meso or SPSA is just guessing one direction of a d-dimensional gradient. And we worked with models that have 66 billion parameters even. So meso should require d times as many steps in that case. But in our case, actually, it uses only 32 times as many steps, even for a 66 billion parameter model. And you can ignore this second line because I don't want to get too much into it. But the key thing is that we need a prompt in a pre-trained model, which is sounding a lot like the kernel view as well, right? So past work has shown that if we use a prompt, then the downstream objective will look a lot like pre-training. Past work has also shown that after you've trained for a long time, the Hessian exhibits the low effective rank. So you're only updating in a very small subspace of the gradient. And finally, there's this insight that you can fine-tune language models in a very low dimensional subspace of the parameter space. So all of this together gives us the assumption that the Hessian has a small effective rank, much smaller than the number of parameters. And thus, we can show that meso is slower than SGD by a factor of that effective rank. So I don't want to dwell too long on this. It's a very practically useful method. Mathematically, what's interesting about it is basically that actually, if we are working with fine-tuning, we can get away with like really like loose approximations. And fine-tuning is really something that people are interested in these days because Facebook or somebody will release a monolithic model And maybe you have your own data set, your own private health data set, or something like that that you need to fine tune on. So I just want to leave it at that. So overall, I want to say it might actually be easier for theory to characterize what's happening when we're training massive, powerful models. So theory may actually be getting easier, which is the experience of my PhD, I guess. And what's next is maybe a precise characterization of the benefits of scale. Given that everybody wants to scale up, what can we say about the benefits of scaling up? Theoretical characterizations of other like LLM type methods. And if you're familiar with these, then great. If not, then I would say don't really worry about it too much. And the development of more efficient algorithms. So are there any questions on this last pre-training fine-tuning part? I know I went pretty fast.
I have questions from much earlier, but is it the end of the talk, or do you have more slides?
I just had one more slide, which is like ambitious questions. Ambitious questions are, I think I mentioned a couple of these, but one that I'm kind of interested in is like, can we build a rigorous characterization of data and how that influences network training? Many optimization analyses will start from like a Gaussian data or something like this. And having some more rigorous characterization of data could be very useful, especially as data quality seems to be a very important factor in network performance. I mentioned this before, but I mentioned this before. So transferring per parameter knowledge to build a human readable interpretation of networks and understanding the role of early stage training are both good directions. And I put my email here. So maybe I'll just answer these questions that are in the chat first. So can you explain a bit more about why Meso works? I don't understand how optimization is happening. Yeah, that's a good question. So optimization in Meso, so what we're doing is instead of performing backpropagation to get the gradient of the loss with respect to the model parameters, we're estimating the gradient using these two forward passes. So once we get this gradient estimate, we can plug that into SGD or Atom or any optimizer. So that's one thing. If the question is more like, this is a very bad gradient estimate, it's just along a random direction, how can that be useful? Then I would say that this is kind of our point with this analysis, where like actually the gradient, you don't need a very high fidelity estimate of the gradient because it's not operating in a very large subspace. It's not modifying all the parameters or making fundamental changes to the network. Hopefully that answered the question.
Can I just ask about that Meso working optimization? I actually wanted to ask, when you're fine tuning, you said you require a prompt and this. So basically, you're freezing the model, right? You're basically just in LoRa and everything, we update the parameters and the whole model changes. And the Meso, like, does it work? Does it really change it doesn't change the model at all? So I'm a bit confused, like with the gradient estimate, it just looks like more of like prompt tuning you're doing. Is it like more of
I can
prompt?
answer that. Yeah. So when I say the prompt is crucial, I mean like any prompt, a simple prompt is crucial. And what the prompt is functioning to do is not to like try to mystically draw out some like pre-training knowledge from the model. And actually the prompt is fixed, so it's not changing. So I like literally the prompt was for some of our experiments. And so basically the way that the prompt works is that you pick the prompt and then you pick some label words. So you pick like great and terrible to correspond to positive and negative labels. So once you do that, you actually do still backpropagate and train the entire network. You get a loss and then you train the whole network. The prompt itself is fixed. It's like a fixed string that you're just adding to every text input that you give in. So in the case of Meso, this is not prompt tuning because the prompt itself is fixed. What we're doing is you get some output, you get some distribution over great and terrible, compute the cross entropy, and that's what this L function is. So this gradient lies in the same dimension as the model. So it has 66 billion entries in it, and it does operate on the model parameters themselves. Now, one thing that you could say is like, is this is it the case that pre-trained models are so strong that once you add this prompt, they actually just solve the downstream task? Maybe that's what you mean. And to that, I would say no. For the tasks that we are testing, like in the meso paper here, these are superglue tasks. So you can see they're pretty far from like actually solving. And so the improvement over zero shot is pretty apparent. So it is actually doing some optimization.
Yeah, thank you so much. That's interesting. Thank you so much.
Yeah, yeah.
Maybe a quick question is, I've very much enjoyed a grokking rabbit hole over the last kind of 2 or 3 months. And I was wondering if your kind of phase 2 SDE says something about grokking.
Grokking. Wow, that's a great question. I wish that I could say yes. Like, I really wish that I could say something meaningful about grokking. But yeah, grokking is one of those things I think that needs to be like truly done from the ground up, like start from matrix factorization or something like this, and then slowly build up. I don't know. Yeah, because ultimately, like I would say, it's a happy coincidence that the SDE gives you some insight into test accuracy, but the test functions that you provably preserve with the approximation are not test accuracy. They're like gradient norm or something like that. So that also kind of makes it difficult when something like is behaving so discontinuously to say that the SDE can really prescribe it. I'm not sure.
And I guess it's kind of to one of your final questions of like some kind of theoretical understanding of generalization is a major challenge.
Yeah, exactly. Yeah, it's interesting that like we've kind of I do feel in a lot of ways deep learning theory is like people have some toolbox and get some conclusion, but to make these conclusions fit together in like a coherent story is still very much like an open and difficult thing. So I may say, you know, I have this theory on the manifold of minimizers that this limiting diffusion is what's bringing about generalization. But someone else may say, like, look, I just worked out like 10 steps of SGD and the gradient noise does such and such. And that is in the early stage of training. And then I don't know, like, where do I fit that in? Does that even show up in my SDE? Probably not, right? So yeah, like I think this is really the plague of deep learning theory is like you have some toolkit, some set of things that you're very familiar with, and you kind of wish that you could make a comprehensive story, but so far it has not happened, I guess.
Thank you.
We can
Yeah,
thank
sure.
the speaker first.